All right, so this video is going to go over pages 10 through 12 in your working energy packet. So we're talking about force versus displacement graphs, which is not going to take us very long. Okay, we did force versus time graphs in the last unit where we found impulse momentum. Well, now what we're doing is we're finding work on a force versus displacement graph. So work is the area under a force versus displacement graph. So basically we just need to find the area on a graph, and that's about as hard as it's going to get. So if you need like a little recap, if you want to find area of a square or rectangle, it is base times height. And if you want to find the area of a triangle, which is half of a square, it would be 1/2 base times height. So I have a graph over here. My force is on my y-axis. My x-axis is my displacement. How much work was done by moving the object from a displacement of 6 meters to a displacement of 10 meters? So I want to know how much work was done in this amount of time. Okay, so I'm looking for the area of that section of the graph. So work equals force times distance, okay, which my force is my y, or so you can do rise or your height, base times height. So your height would be 2.5. Your base, it goes from 6 to 10, that is 4, so be careful with that, don't put 10. Okay, your base would be 10, so 2.5 times 4 gives you 10 joules, and that's all you had to do. Number 2, how much work was done by moving the object from 0 to 20 meters? So I need to figure out what is the area of this big rectangle. So 20 times 100 is going to give me 2,000. So that is going to be my answer for part A, so 2,000 joules. How much work was done by moving the object from 20 to 30 meters? Okay, so now I got to figure out how much was that triangle worth. So I have a base of 10, a height of 100. So 10 times 100 is 1,000. Half that, since it's a triangle, that makes this 500. So this would be your answer for part B would be 500 joules. And if I want to know how much total work was done during that displacement, all you got to do is add that up. So you get 2,500 joules. Okay, moving on to the next page. So the reason why there was so much space and stuff on here is we originally had you draw graphs. Okay, that's why the directions are so in detail of what's going on. But for the sake of time's sake, we're just kind of focusing on letting you read graphs and just solve for work. So I have a graph here. My force is on my y-axis. My displacement's on my x-axis. So I'm trying to find the area of this graph. Okay, so what I'm going to do is I'm going to split this into a square and 2 triangles. So my first triangle is a base of 1, a height of 2. So 1 times 2 is 2. Half that would be 1. My square has a base of 2, height of 2. 2 times 2 is 4. And the other triangle is the same thing. 1 times 2 is 2. Half that is 1. So it would just be 1 plus 4 plus 1. And that gives you 6 joules. Okay, moving down to the next graph is we're going to find the area of this graph. So even this one kind of stops dead in its tracks. We're still going to find the area all the way down to the x-axis. We're going to find the area underneath that line. So I'm going to split this up into a square or rectangle. It honestly doesn't matter how you do it. As long as we get the same values, I do not care. So that first square has a base of 5, height of 40. So 5 times 40 is 200. And it's not a triangle anymore, so don't half it. Okay, and then you have your other square. You have a base from 5 to 15, so that's 10. 10 times 20 is 200. Okay, so 200 plus 200 is going to give you 400 joules. So that's how much work was done on that graph. Now on this graph, this one is a little bit wonky just because, as you'll see here in just a second, we're going to find the area of each little section. So if I want to find the area from 0 to 8 meters, I need to find the area up until that point. Okay. So my first box has a base of 4, a height of 5, so this would be 20. My next one is the same, so base of 4, height of 5, that's 20. My next box goes from 4 to 8, so that's a base of 4, height of 5, that's 20. So this is what I mean by a little bit wonky is the boxes don't look the same, okay, even though they're the same value. Not that great of a graph, so I don't know why we have this one, but just go off the numerical values that are on there. So my base for my triangle on top, so it's a base of 4, a height of 5. 4 times 5 is 20. Half that is 10. Okay, my next box goes from 8 to 12. That's 4. 4 times 5 is 20. And then my triangle has a base of 2. 12 to 14 is 2. 2 times 5 is 10. Half that is 5. So if I want to figure out how much work was done from 0 to 8 meters, I'm going to add everything up until 8 meters. So that's 20 plus 20 plus 20 plus 10. That means 70 joules of work was done. For B, now I want to find the whole thing. So I'm going to go ahead and start on that 70 and just add on to it. So 70 plus 20 plus 5, that means 95 joules of total work was done. Okay, so that's basically graphing. That's about as hard as it's going to get. So you'll probably see one problem on that, and that's probably about it. So if you can do that part, that should be an easy point. Now, this is the stuff. Now we're back to work stuff. So this is where, if you're struggling with stuff, make sure you're paying attention here. So what we're going to do is we're going to calculate the amount of work done by the appropriate agent in each of the following cases. Now, in a quiz, we would be very specific of if I asked for the work of a car doing this, or if I asked for what is the work that friction's doing, or if I asked for what is the net work doing, what's the total work doing, okay, we'd be very specific. This one wasn't that specific, so I'm going to show all the possible works that are going on. Okay, but normally on a quiz and stuff, it would be specific, like tell me exactly what is this work being done. So let's give it a shot. So calculate the amount of work done by the appropriate agent in each of the following cases. A workman exerts a horizontal force of 30 newtons. There's force to push a 12 kilogram table across a flat floor. So we have a mass, okay, a distance of 4 meters. So there's your distance. So since I'm not lifting this table up, mass really doesn't even matter. Okay, so if I was, then mass would definitely matter because now gravity is going to affect it. So in this case, I have a force, I have a distance. So work equals force times distance. So all you got to do is 30 times 4, and you get 120 joules of work. So that one's pretty simple, nothing too crazy there. A horse pulls a sled 12 meters, so there's your distance, along the ground at a constant speed of 2.0 meters per second, there's a velocity, against a frictional force of 1,500 newtons. Okay, so you have a force of negative 1,500 newtons. That's how much friction is doing. Okay, so what I'm going to do is, this is what I mean by we weren't really specific on what type of force or what work is being done, so I'm going to show everything. So key term here is the horse is going at a constant speed. Okay, constant speed means everything's balanced. So that means whatever the frictional work being done is going to be matched by the actual work the horse is doing. So for now, let's just figure out how much work is friction doing. Okay, so the friction, okay, so we're going to do work for friction. So let me clear that up real quick. So work for friction equals the force of friction, which would be negative 1,500, times the distance, which is 12 meters. Okay, and that gives you negative 18,000 joules. So if I asked you how much work friction was doing, that would be your answer and you'd be done. Okay, so that is one possible answer there. Is if I asked for how much work the horse was doing, okay, constant speed means the horse is applying the exact same amount of work, just the opposite way. So the work of the horse would be a positive 18,000 joules. Okay, so that would be the work done by the horse. Now, if I asked you what was the net work, okay, net work means you combine every work that's going on. So we have the work the horse is doing and the friction work. Okay, that means 18,000 minus 18,000. My net work would actually be 0. Okay, because they basically cancel each other out. So you can have individual works where they actually cancel out, where you have a net work of 0. So again, on a quiz or a test, we would be very specific on what is going on there. C, a man exerts a force of 150 newtons parallel to a slope to slide a 50 kilogram mass 8.0 meters up the slope. Okay, so the man is exerting a force parallel to the slope. Okay, so force and distance have to be in the same direction. In this case, they both are. Okay, so no one is denying that he's applying this force over this distance. Okay, so that's how much work he's doing. That's how much force he's applying. So all we gotta do is calculate how much work he's doing. So work equals force times distance. So my force is 150 and my distance is 8. So 150 times 8 is going to give me 1,200 joules, and that would be your answer there. Okay, now would mass matter with pushing something up a slope? Yes, it would. But that's not changing the fact that he's applying 150 newtons of force to the object for 8 meters. Okay, so mass is a factor, okay, but he is applying the same amount of work no matter what the mass is for that distance. So that's why we didn't really care about the 50 kilograms. Now, the D, it says a 1.6 kilogram block is lifted vertically at a constant speed of 1.2 meters per second through a height of 20 meters. Okay, so work equals force times distance. Okay, mass is not a force. So 1.6 kilograms is not a force, but weight is. If you're lifting something, weight matters. So force is now mass times gravity times your distance. Okay, so that is your work when you're lifting something. So my mass would be 1.6. Gravity would be 9.8. Since you're lifting it up, that's why 9.8 is positive, because gravity is not the one doing the work. If it was gravity was pulling this block down, like actually like if you drop the block and gravity was doing the work to pull it down, then it would be negative 9.8. But it's positive in this case, and your distance would be 20 meters. So multiply that out, and you get 314 joules of work. All right, a girl pushes a skateboard forward with a thrust of 120 newtons against the frictional force of a sidewalk of 40 newtons while moving 2.5 meters. So you got a couple things going on here. Is you can combine these, you can separate them. If I asked you what amount of work was the girl doing, just the girl, okay, nothing would change the fact that her force is 120, and she's applying at a distance of 2.5 meters. Okay, so the girl is doing 300 joules of work. Now friction, okay, so the work of friction, no one's denying that it's negative 40 newtons, okay, and that's also for 2.5 meters. Okay, so that would be a value of negative 100 joules. Okay, so that would be the work of the girl and friction individually. If I asked for what was the net work being done, then you would combine those, so 300 minus 100, and that would be 200 joules. So again, these are all viable answers, and we would be pretty specific on what we want. So those are your options there. Number 2, from what height must a 10 kilogram hammer fall in order to do 240 joules of work on a stake being driven into the ground? Hint, the gravitational force must first do 240 joules of work on the hammer. So that means, all that means is we have our work. Okay, we're looking for how far it must fall. Okay, so that means you're looking for distance, so work equals force times distance. And since something's falling and we have a mass, then we're going to go ahead and say mass times gravity times distance. So I already know work. Work is 240. Your mass is 10. Gravity's doing the work here, so that's negative 9.8. And distance, we don't know. We're going to leave that as D. And you get a value of negative 2.45 meters. So it is okay to get that negative because mathematically all that's stating is that's how far it fell, was 2.45 meters. But if you put positive 2.45 meters, that's fine too. Okay, but that would be your answer. 3, calculate the amount of work done in each of the following. A gardener pushes down on the handle of a lawnmower at an angle of 45 degrees with an applied force of 141 newtons. Okay, while pushing the mower 8.5 meters along level ground. Okay, so we have a lawnmower, of a person pushing down on a lawnmower at an angle of 45 degrees. Okay, they're applying 141 newtons of force along that angle. Okay, but my lawnmower is going this way. Okay, just purely horizontal. That 141 is not purely horizontal, so that's why we cannot mix 141 and that 8.5, because that 8.5 meters that the lawnmower is traveling is only horizontal. So we need to figure out how much that 141 is horizontal. This is where we get to find the whole Fx. How much force is on the horizontal plane, which is the adjacent side. This is basically a triangle. So it means you're looking for the adjacent side of your triangle. So remember, cosine of your angle equals adjacent over hypotenuse. If you're looking for adjacent, go ahead and multiply both sides by the hypotenuse. So that's what we're going to do. So Fx, which is your adjacent, equals your hypotenuse, 141 times cosine of 45. Make sure you're in degree mode, and you get 99.7 newtons. So that is how much force is actually going in the horizontal direction. That matches the 8.5 meters that the lawnmower is going. Okay, so now we have our force, and we have our distance, so we can calculate work. Work equals 99.7. Distance is 8.5. That means there's 847.45 joules of work. B, a 40 kilogram girl on skates is swung through one revolution in a horizontal circle at the end of a 10-meter rope held by a stationary boy at the center of the circle. The rope has a tension of 50 newtons in it. Okay, so this is circular motion. So remember, we talked about circular motion is if this boy is spinning the girl around, okay, the force is always directed towards the center, okay, but the distance that she's covering is always tangent to the circle. So no matter where you are, so even if that girl was up here, her force would be down here towards the middle, and her distance would now be going to the left. Okay, so no matter where you turn her, okay, her force and distance are never going to align. Okay, so her force is perpendicular to the distance being covered. And if those are perpendicular, then technically no work is being done. And that'll end that one.